Okay, now it's set to record. So we've got our base formula here. Is this is what everything's going to be based off of. This is how we're going to figure everything. So whenever we we lay out our sprinkler system and say we have a simple tree that runs like this, you got heads here, here, and here. Now, if you guys have questions on anything, please stop me because I'll blow through a lot of this. I've taught this about 10 to plus times, and so I just kind of run over it. And I'm assuming you guys have been doing design for a while, so some of this should be relative norm to you. Whenever we're trying to figure out what is the minimum flow coming out of a given sprinkler, well, we just take our area, which is often shown as an A sub S, and we multiply that by the density, which, you'll see often is 0.1, 0.2, 0.15, whatever it is based on our hazard. And that is going to equal our Q or our flow. Okay. Pretty simple. As area is just square root and density is GPM or area square foot, density is GPM per square foot. So you just come out with a GPM as your units, a gallons per minute. Do you guys all understand just how to get your simple Q based on a sprinkler layout? We all good to move forward on that? Okay. Everyone's quiet, so I'll assume that's a yes. Oftentimes, depends on what calc program that you're using. I hope most of you guys are on AutoSprink, and for those of you that aren't, I feel sorry for you. But if you ever have to figure out what the pressure is at a sprinkler, what the minimum pressure is. So let's say we've got this sprinkler right here. We'll just do assume this is like a warehouse, a simple tree. We'll say that our sprinklers are spaced at 120 square foot and the density is 0.2. Okay. So these sprinklers here all have 24 gallons per minute. That's just 120 times 0.2. GPM, and I apologize for how bad I write with the mouse. Now, if we need to figure out what the pressure is at that sprinkler, all we do is we go over to this formula here, and everything comes off of this base, Q equals K square root of P. So we just manipulated it around, and we'll take our flow, which is 24 divided by, let's assume that these are K 5.6 sprinklers. And we'll also show what happens when you change K factors. So we take 24 divided by 5.6, hit equals, and then hit squared on your calculator, and that comes up with 18.4 PSI. Now, what happens if we change the K factor on these heads? What should happen to the pressure? And this is often why we use different K factors in different sprinkler systems. Yeah, so this is with the K5-6 head, it's 18.4. If we do this exact same thing, if you take K8, okay, and go 24 divided by 8 is going to be 3, square that is 9. So a K8 sprinkler cut your start pressure in half. That's where, when you're doing these drawings and figuring out what kind of sprinkler to use, depends on what pressures that you have that you're working with. You can see it's slightly bumping up the K factor, cut my start pressure in half. So that's just some things to take away is how this K factor relates to choosing your sprinkler and what your starting pressures are and what your flows are. Okay, now we're going to run through a basic setup here. So we figured out what our flow is at this. It's 24 GPM. Let's say that we've got a perfectly symmetrical tree. So this is 10, 10, and this will be 5 foot here, 5 foot here, and we'll say that we're 12 foot between lines. Okay, and everything's flat. There's no riser nipples, nothing like that. We're just going, everything is straight flat. So we need, let's say we have to figure out what our minimum pressure and flow is at this point right here. So if I take, I want to know, sorry, I'm trying to make, okay. I want to know what my pressure is at this point right here. Okay. So the way we figure this is we just take our starting pressure. We got to figure out what our friction loss is through here. And then as we hit this with bigger pressure, we get flow. We add the flows, figure out the friction loss, boom, going back until we get to a point here. So let's do some more assumptions on this. Is that this is 1 inch, 1.25 inches, and 1.5 inches. Okay. And for grins, we'll say that this is 3 inch for the main. We're going to assume that everything is schedule 40 right now. It just keeps a simple, it keeps everything simple. If we do this again and go into more depth on some things, we'll go over what you do when you've got like schedule 10 piping. You've got to figure out different equivalent lengths and stuff like that, or if your C factor changes, things such as that. So we are using black steel and it's wet. Okay, so the basis of this whole thing is there's a formula to find the friction loss per foot. This is in your NFPA 13, 4.52. Sorry, let's see if I can, I don't know how to erase. Let's fix this for you so it just looks a little bit better. 4.52 times Q to the 1.85 divided by C to the 1.85 and then D to the 4.87. Okay. So if you're going to enter these in your calculator, if you just remember the order of operations, I'm going to try to do something here. Let's do this. Let's say that this is A, just so I can write something easier. C and D. If you're going to put this in your calculator so you can do it real nice and easy, not have to do all parentheses and stuff, you're going to take A times B divided by C divided by D. Do you guys understand this? I've taught this in some of these classes and people can't grasp this concept with your calculator. You guys okay on that basic algebra? It's just order of operations. If you're good with that, we can keep moving forward. Okay, I'll assume that silence is a yes. Okay, so what we're trying to do is to figure out what our friction loss is to flow 24 gallons from this point to this point here. I'm going to try to find a different color and say, so I lost my mouse, there it is. This will be node 1, 2, 3, and I'll share this note thing with you guys so you've got my notes and scratches on here as well. And we are recording this so you can go over it again if you ever want to. That is a 3. Okay, so we need to find the friction loss from 1 to 2. Okay, so we need to know what our friction loss is through here. Our starting pressure is, or our starting flow is 24 gallons. So we look in this formula right here. So we have 4.52 times 24 to the 1.85 divided by black steel pipe. What's the C factor for a wet system with black steel pipe? I assume you guys know this off the top of your head. Okay, yeah. And then the diameter of 1 inch schedule 40, 1.049 to the 4.87. So this is going to give us the friction loss per foot. So let's all plug this in our calculators. I want to make sure we all get the same answer. So we do 4.52 times 24. You should have a y to the x button, which I haven't used this calculator to find my y to the, there it is, to the power of 1.85 divided by 120 to the power of 1.85 divided by 1.049 to the power of 4.87. What do you guys get as the friction loss per foot? I got 0.18. What did anyone else come up with? .52 times 24 to the power of 1.85 divided by 120 to the power of 1.85 divided by 1.049 to the power of 4.87, and I get 0.18. Does anyone else want to confirm that? .18? Okay, cool. So this is per foot. So it's 0.18 per foot. Okay, we said that this was 10 feet going through here. So this is going to give us times 10 feet equals 1.8 friction loss from 0.1 to 2. Okay, so if there is 18.4 psi to start, as I've got to have 18.4 here to get 24 gallons a minute out of this half-inch sprinkler. I'm going to lose, or I need 1.8 psi to overcome the friction loss that occurs between these 2 points. That means that this head right here must have 18.4 plus 1.8 or 20.2 psi. Do you guys see that? Okay, so now we got to figure out how much water is flowing through from point 2 to point 3. We know it's 24 GPM is the minimum, but we said that your flow and pressures are directly proportional. So if I have 20.2 pounds now hitting this outlet right here, I should get more water. So if we go 5.6 times the square root of, we said 20.2, right? 20.2 equals, now I get 25.2 gallons per minute coming out of 2. Do you guys see that? Do you follow how I got 25.2 coming out of there? We all good? Okay. So now what we have to do is figure out the friction loss from point 2 to point 3. So friction loss from 2 to 3 is what we're trying to figure out. Flowing through here, we've got 24 gallons plus whatever was coming out of 2. So our Q from 2 to 3 is going to equal 49.2. Does that make sense? We just added the flow here plus the flow come out of this head. So that's how much water's got to go through this piece of pipe. Now we got to figure out what our friction loss is. So we use this same formula here, right here. So we'll do 4.52 times, now it's 49.2 to the power of 1.85. Geez, I can't write very well there. Over 120 to the 1.85. And then inch and a quarter, schedule 40. Yeah, we said this was inch and a quarter. So that's 1.38. 38 to the 4.87. Right? Yeah. So you guys got that figured out? You can tell that I'm like turning my head because I'm writing all sideways. So what does the friction loss per foot work out to be here? Let's see if Scott can get this right this time. We take 4.52 times 49.2 to the power of 1.85 divided by 120 to the power of 1.85 divided by 1.38 to the power of 4.87. And I come up with 0.18 again. Do you guys all come up with the same? 0.18 or, okay, then, yeah. Then times 10 feet gives us 1.8 PSI from 2 to 3, okay? So our starting pressure at point 2 was 20.2, and now we got to add 1.8. So our pressure at 3 equals 20.2 plus 1.8 is 22. Is that right? Okay. Now we got to figure out what is the flow coming out of point 3. So we'll say that the flow coming out of 3 is just K times the square root of P, which equals 5.6 times the square root of 22. Q3 equals 5.6 times square root. I lost it. You get 26.3. Okay. Now, we got to figure the friction loss from 3 to 4. This is just 5 feet, but what's the flow going through here? We had, what was our flow in the last one? I didn't write it down. We had 24 here. And then what was our flow at point 2? 25.2. So our total flow was 49.2. So now our flow from 3 to 4, Q3 to 4 equals 49.2 plus 26.3. And what does that come up to? 75.5? I'm trying to do that in my head. Is that right? Okay. Now, we know our starting pressure at 3. We know our flow going through here. So let's figure out the friction loss per foot. You guys see this just the same thing over and over and over and over again? P from 3 to 4 equals, I'm going to try to do something here, see if this will work better. 4 point, is it going to let me do it? No, it doesn't. I thought it would let me write it in. No, it doesn't. Let's just do pen. Okay, so let's close that. Okay. 4.52 times 75.5 to the 1.85 over 120 to the 1.85. And then our diameter, what's our diameter of 1.5 inch schedule 10 or schedule 40? Does anyone know offhand? I don't, so I'll cheat. Using auto sprink, the diameter is 1.61. So we go 1.61 times 4.87, or to the 4.87. Okay, so what does this friction loss per foot come into? 4.52 times what? 0.189. So say 0.19. Does anyone else concur with Scott? We got to kind of... Okay, cool. Then I'll take it if two people get it. So now the total friction loss in that piece of pipe there's 5 feet of that. So 5 times 0.19 is 0.95. So friction loss from 3 to 4 is 0.95. So then our total pressure at 0.4 is just the pressure at 3 plus the friction loss going through there. So our pressure at 3 was 22.2. Add our 0.95. So our P total is just 22.95. Do you guys get that? This is kind of the basis of everything you're going to do. And I'll show you the next steps we do here is we're going to add in a couple fittings and do some equivalent K stuff. But if you can do this, you can do foam systems, because you'll come into, this is how you learn and how to apply this stuff into the crazier things. But do you guys follow just a simple plug and chug of how this was done? Okay. Is there anything that's confusing and not making sense? Because it's just basically... Yep. Yeah, and what you have to do, and the problems with NICET will all be set up this way, is that you have to verify that you're getting the minimum flows out of each sprinkler. So let's say that this one had a minimum flow of 20 gallons and this one had a minimum flow of 24. Well, we may not have had enough flow coming out of here, and so you have to do some different iterations. That gets more into like your level 4 type calcs. So, and actually back when I took it, is they didn't even have stuff like that. Is you just need to make sure that whatever flow you come up with coming out of like 0.2, is that it satisfies the minimum required. We said each head had a minimum of 24 gallons, and every Q that we developed, 25.2, then there was another individual Q there of 26.3. We were always in excess of 24 gallons. And with this, you can kind of see something. You start to look and get an understanding as you grasp things, is that this is why you will never get, like if you're doing 0.2 over 1500, you will never get 300 gallons per minute exactly, because there's going to be some friction loss somewhere. And anytime there's friction loss, that means that there's greater pressure at the orifice closer into the system. So with greater pressure, it's going to cause bigger flow. So again, you know, your flows are never, this is why you don't ever get a perfect theoretical, you know, 0.1 over 1500. You're never going to get 150 gallons for your system. You're always going to get something more than 150 gallons. And that's just because every time you run through a piece of pipe, you've got to account for that friction and that pressure. That pressure hits the same size hole and it adds more flow to come out. Does that make sense? There's something that, if you don't understand what all this is doing, is there something in NFPA 13 that says that you can't use the K factors to balance out the flows? So if we were to do this with an 8.0 K factor, here, let's try that. Let's do this exact same thing with an 8.0 K factor. Let me just start a new page. So we'll do, we've got our pipe here. We're going to go head, 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 and we're going to do that one twice. We're going to do it with two different things, and I'll show you what's happening. Okay, so this is 24 gallons, K8. K8, K8. Let's just do inch, inch and a quarter, inch and a quarter. Okay? So what is the friction loss from, oh, here, let's make nodes. 1, 2, 3, 4. I didn't know I was writing in rainbow colors. Jeez. I don't like that. Hold on. Let's go back to that there. Okay. Now this will be 10 foot, 10 foot, and 5 foot. We're keeping these all basic numbers just to make it easy. So our friction loss from here to here, we do 4.52 times Q to the 1.85 over C to the 1.85 D to the 4.87. And yes, I know it's horrible that I have that damn formula memorized. Okay, so from point 1 to point 2, what's the friction loss from point 1 to point 2? Do 4.52. Oh, wait a minute. Let's figure out something first. I should have done this. What's our starting pressure coming out of this head? Because now we got a K8 sprinkler. So I always got to do Q equals K times the square root of P. So P equals Q divided by K squared. So P equals 9. Do you guys follow that? 24 divided by 8 is 3, squared is 9. Okay, so now what's the friction loss going through this piece of pipe? 0.18, good, okay. Now, what is the, so this is 0.18. So now what's the pressure at this point here? It's 9.18 because we had a starting pressure of 9. Oh, sorry, yeah. So, yeah, it's 10.8. My apologies. 10.8 equals 1.8. Yeah, it's 10.8. Okay, so now let's figure out what's the flow coming out of here. So we'll say Q equals K times the square root of P. So we have 8 times square root of 10.8. I did that wrong. 8 times square root of 10.8. You get 26.3. What? Yes, yes. Yeah, we're doing K8s for this one. Hang on just a second. Okay, so did you get this 26.3? Okay. Okay, so now we got to find the flow going through this piece of pipe here. So the total flow is 50.3, right? As I just added the two together. And now we need to find the friction loss in this section of pipe. So the friction loss is just this formula here again. So we do 4.52 times 50.3 to the power of 1.85 divided by 120 to the power of 1.85 divided by 1.38 to the power of 4.87. And I come up with 0.18 again. Yeah, which is very similar to what we had, or actually 0.19. Okay, times 10 is 1.9. So now the pressure here is 10.8 plus 1.9, or 12.7. Do you see that right there? Okay, so now we got to figure out the flow coming out of here. You just do Q equals K times the square root of P. So we do 8 times square root of 12.7, and that equals 28.5. Do you guys get that? Okay, cool. So now the flow going through this segment of pipe is going to be 28.5 plus 50.3, or 78.8. And so now what is our friction loss through this segment of pipe? So 4.52 times 78.8 to the power of 1.85 divided by, divided by 120 to the power of 1.85 divided by 1.38 to the, no, that's inch and a quarter there, 4.87. I changed it up just a bit on you. It's 0.43, and then times 5 is 2.16. That's for the 5 feet. So now my total pressure at 4 is 12.7 plus 2.16, or we'll say 2.2. So we got 12.7 plus 2.2 is 14.9. So what I want you to see is this number here and this number right here, because we're going to change these suckers by doing Okay, sorry, Scott just told me that I got muted. I hit the mute on my button. So we're going to do this exact same formula again. As we got K.8 and or a K8 head and a 24 gallon start pressure. Everything's the same up here. The only thing that's changing is this sprinkler is going to be a 5.6. So we got 24. It's going to be the same friction loss, 10.8. We got the same thing coming through here as our friction loss is 1.9. So now we get P is 12.7. Do you guys follow me here? That it's just all the same now? That we've done everything the same up until this point here. Is that cool? Okay, now we got to figure out Q here. So Q, let's say that this is like a, well, no, let's just keep it all the same. So Q equals K times the square root of P. So we got 5.6 times square root of 12.7 is basically 19.9. Let's just, as I'm going to throw another variable in here that I meant to put in, and I didn't put it in until the end. This one was covering, say it was covering 90 square foot instead of, these were all covering 120. Okay, 120. We're at a 0.2 density, but for whatever reason, due to walls or whatever, this one was covering 90 square feet. This head here was 90 square feet. Okay, so its minimum, its Q min is 18 GPM. Do you follow that? 90 square foot times 0.2. Okay, now we've met the criteria is that we have to make sure that this head can meet or get its minimum discharge. It's only kicking out 19.9 gallons versus the 18 that it needs as a minimum. But here's where you see the big difference. See, this was 19.9 gallons here, 28.5 gallons here. So what that's doing is you're basically trying to throttle down the system, and NFPA because this can get real confusing as far as maintenance and stuff goes, is say you got a big open warehouse or, like a big open room, you got heads here, here, and here. You got a K8, a K8, a 5.6, and a 4.2 because you're trying to balance down the flows with your K factor. NFPA 13 says you can't do this because what's going to happen when the building changes hands 2 or 3 times and this head has got to be replaced, they're going to get the wrong head in it, or, they put a 4.2 instead of a 5.6 here. Things aren't going to work. So this is what happens when you mix the orifices, and this is where NFPA says, no, you can't do this because you're trying to balance, you're trying to cut down your flow, give your system less flow so your calcs have less pressure loss coming to this point. And that's the rationale as to why they're saying that you can't use K factors to balance flows. Does that make sense? Okay, cool. So a lot of guys don't understand that. It totally blows them away. Now, let's do something, the exact same thing. So we've got our main here. We're going to do something a little bit different though. Head, head, head. Now we're going to add extra branch lines. Okay, and because we've added extra branch lines, now we're going to take our flow down to this point right here. This is our question mark point. We want to know what is needed. What is P here and Q here? At this point, we're going to say that each sprinkler is, let's do it, 18 GPM. And let's do a 5.6K, okay? This will be 1 inch, 1 inch. Yeah, let's just make it really crazy. 1/4. Okay, 10 feet. I'm just doing the 10s and the 5s for easy math. This will be 3 inch schedule 40. And the only reason why I picked 3 inch is because I know the internal diameter of 3 inch schedule 40. So we're going to have to figure out what the flows and stuff is here. This is where we're going to start throwing in fittings. We're going to learn how to choose the fittings that we do. And we're going to learn the concept of an equivalent K factor. So let's say that this is 12 feet here. 12 feet, and then we'll just say that this is 6 feet just because it's halfway through or something. Let's node this up as node 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, you guys follow this simple node pattern. One thing, if you've noticed, well, let's work this through and then I'll come back and explain something with the math that I think is cool. You guys may just think I'm a nerd, which is fine. So let's figure out what our friction loss is from 1 to 2. So that's our same formula, 4.52 times 18 to the 1.85 divided by 120 to the power of 1.85 divided by 1 inch schedule 40 is 1.049 to the power of 4.87. So I get, let's just say 0.1 pounds per foot loss. And so now my pressure at 2, my P2 equals 10.1. Do you guys get that? Nope, times 10 is 11. Sorry. My pressure at P2 is, I'm sorry, I totally blew this on you. The friction loss here is 0.1. What is our starting pressure at node 1? That's what we didn't figure out. How do you figure that out? So you get Q equals K times the square root of P. So P equals Q over K squared. So what is P1? 10.3. Okay, we figured the friction loss in here was 0.1 pounds per foot times 10 feet. So our pressure from 1 to 2 equals 1 psi, right? 10 times 0.1 is 1. So P2 equals 11.3. Okay. Now, let's figure out what we said. Q1, I'm going to try to write these here. Q1 is 18. What is Q2? So we got 5.6K heads times square root of 11.3. I get 18.8. Do you guys get 18.8? Yes, no, maybe? I hope I did that right. Should be right. 5.6 times 5.6 times the square root of 11.3 equals 18.8. Yes. So the flow going through here is 18.8 plus 18, or 36.8. So we need to find what is P3. Whoops. I'm trying to keep the colors consistent so when I save this for you guys, you can have it. P3 is going to equal what? We've got to know the friction loss going through here. So our flow is 36.8, our diameter is 1.049, and we know our C is 120, so we can figure out what this is. So 4.52 times Q, 36.8 to the power of 1.85, divided by C, 120 to the power of 1.85, divided by the diameter, which we're doing 1 inch again, to the power of 4.87, and I come up with 0.4 pounds per foot. Do you guys come up with 0.4 pounds per foot? Okay. So the total is 4. So that times 10 equals 4. So our friction loss in here is 4. So our P3 is 4 plus 11.3 is 15.3. Now we got to figure out what is Q3. Equals, so I got just Q equals K times the square root of P. So we do 5.6 times square root of 15.3 is 21.9. Do you guys follow that? Okay, so now the flow from 3 to 4, as I add up all three of these, or 36.8 was the flow here, plus the flow coming out of this is 21.9. So 36.8 plus 21.9 equals 58.7. So 58.7 is the flow right here. Do you guys see that? Okay, so I haven't lost anyone yet. Now we got to figure out what our friction loss is. So we just do 4.52 times 58.7 to the power of 1.85 divided by 120 to the power of 1.85 divided by friction loss, or our diameter. So now we got 1.38 to the power of 4.87, and I get 0.25 pounds per foot. Okay. Yeah. Times 5 is 1.25. So now, let's see here. I'm trying to keep the colors consistent. So we had 1.25 is from 3 to 4, right? So P4 is going to equal, let's call that 1.3 since we've been to 1 decimal point the entire time. Let's just stick with 1 decimal point. So we'll say 1.3. And now this becomes 16.6. Does that make sense? Okay. So we got this here. So we know that our flow, our Q4 is 58.7. And we got P at 4 is 16.6. Okay? If we know, is this formula here is our basis and everything, Q equals K times the square root of P. Well, I know 2 of those values at a given point. I can make up what's called an equivalent K factor. So basically what that's saying is like, what size hole do I need? Because the K factor basically relates to the hole in the pipe. So, let's say I've got a piece of pipe here with a hole like this. Let's say that that's a 5.6 K factor. A hole like this is, like an 8.0 K factor. Well, if I need to push out 58.7 gallons at 16.6, what size hole do I need, or how can I represent that as something? That's where you'll hear the term equivalent K factor. So we can come up with a K EQ of 4 is going to equal, so we say K equals Q divided by the square root of P. Do you follow that? So now if we take 58.7 divided by the square root of 16.6, I get an equivalent K factor of 14.4. Okay? So for these branch lines, so now this is an identical branch line. If I start here, if I got 18 gallons here, and these are 5.6 heads, if I calculate this back, it's the exact same thing. I'm going to need 58.7 gallons at 16.6 pounds right there. Do you follow that? At node 5, I'm going to put an open parentheses of 16.6 right now and an open parentheses Q of 58.7. Okay, that is what I need at node 5 at a minimum. But if I only have 16.6 pounds here, and I need the same thing here, is I need 16.6 pounds here. So you know that the actual pressure at 5 is going to be greater than it is at 4, correct? Okay, so that's why we use these equivalent Ks, is that what I've done is I calculated this line back. This is the exact same line, so I could have calculated this one first. It would not have made a hill of beans difference, whichever one I did. I've developed an equivalent K factor. So I'm saying that the equivalent K factor, basically, if I create a hole in this pipe that is an equivalent of a 14.4 K factor, that's going to give me 58.7 gallons if I hit it with 16.6 pounds. Make sense? Okay. But now let's figure out what's actually going to happen with this. Is at node 4, my pressure at 4 is 16.6 and my flow at 4 is 58.7. Okay? I'm going to change this so it's a little bit more drastic for us. Let's make this be 1.5 inches. I want to show a much more drastic change from what we're going to have. So this is 1.5 inch pipe, and this is 1.5 inch pipe here. Does that make sense? You guys okay with that there? So now let's figure out what the friction loss is from 4 to 5. So my flow at 4 is 58.7. Comprende? And my starting pressure is 16.6. So we're going to figure out the friction loss from 4 to 5. So that is just going to be our 4.52, is our same formula we've been using, times our flow, which is 58.7 to the power 1.85, divided by our C factor. We've been doing a C factor of 120 all along. And that's to the power of 1.85. Oops. Divided by the diameter of 1.5 inches, the inside diameter was 1.61, right? 1.61 to the power of 4.87. So I come up with 0.14 psi per foot. We've been doing 1 decimal, so let's say I come up with 0.1 per foot, right? Per foot times 12 feet equals 1.2. So now my pressure, my P5 is going to equal 16.6 plus 1.2, 17.8. You guys got that? Does that make sense? Okay. Now, what in the heck is the flow coming out of 5? How on earth do we determine that? This is where we use our equivalent K factor that we developed earlier. So we said that in order to get 18 gallons a minute out of here with a 5.6 head, and then get this to here and this to here, we need a minimum of 16.7 pounds at 58.7 gallons. I'm going to hit this with 17.8, so I got to figure out how in the hell do I know how much flow that this line is actually going to output. We developed an equivalent K factor of 14.4. So my Q5 equals the K factor at 5 times the square root of the pressure at 5. So we said my K factor was 14.4 and the pressure was 17.8. Times square root of 17.8. So I come up with 60.8 gallons. 60. I'm going to erase that, make it look a little bit better. Do you understand that? Do you guys see how I got that? And that's because you have to develop your equivalent K factor on your branch line earlier. We could have come back through and calculated all this again, but our Hayes and Williams formulas that we deal with, they give us the ability to create a K factor at any point as long as we know the flow and pressure. Does that make sense? Okay, so now we got to find the friction loss between, hang on. Well, first let's find the flow in the pipe from 5 to 6. How do we figure that out? Our flow from 4 to 5 is 58.7, right? We said that we need 58.7 gallons right here. There's no added flow at 0.4, so it's coming down. And we got, so 58.7 is flowing through here. Now we're getting an additional flow of 60.8 plus our 58.7. So 60.8 plus 58.7 is, our flow here is 119.5. You guys follow that? Yeah. Make sense? Okay, cool. So now let's do the friction loss from, because we're trying to find what is the pressure and flow required at node 6. We already know the flow is 119.5. So if you're taking your NICET exam and there's, 4 choices and 2 of those have, 127 and 136, and then there's 2 with 119.5, you can throw out the other 2 because they can't be right. So now we just got to figure out what our friction loss is from 5 to 6. And that's our standard 4.52 formula. So we do 4.52 times our flow was 119.5 to the power 1.85 divided by, we're still sticking with the 120, to the 1.85 divided by, this is still 1.5 pipe, so 1.61 to the power of 4.87. And your friction loss there is 0.44 pounds per foot times 6 feet equals 2.6. Did you come up with that? Okay, so now the pressure at 0.6 is going to be, we had that the pressure at 5 was 17.8, correct? Plus the friction loss from 5 to 6 is 2.6. So we do 17.8 plus 2.6, and that gives us 20.4. So the pressure here, P is 20.4, and Q was 119.5. Do you follow how to do that? Okay. Let's backtrack just a bit here. This was something that I didn't do. It is now we're going to add fittings into all this stuff. So we need to know where to add a fitting. NFPA tells us that we don't need to do the fitting for a sprinkler that's screwed directly into a fitting. We don't need to include that fitting because that's kind of built into the K factor of the sprinkler. But if we're flowing our pipe here, we have to figure out which fitting, because we're coming to a fitting that changes flow 90 degrees. We need to know how to figure out what fitting that we're doing. So let's do an example like this for a second, where we've got a riser nipple here. We're going this way. We got pipe going like this, here and here. We got a head here, head here, head here. And we're going to put nodes. All we're going to do now is just talk about what fittings go on these things. Let's put a node here and a node here. Okay. Guys get how to tell which fitting goes on what pipe wrong all the time. So we calc everything backwards. Okay. So we start from the end head and come backwards, starting out. That's our demand calc. So what we're figuring out is what is the absolute minimum flow and pressure we need to make things work. But the way that we figure the fittings into these formulas is that the pipe is going, or we're running our calc back this way. So there's no fitting between 1 and 2. There's no fitting between 2 and 3 because our pipe didn't change 90 degrees. Now we come here to 4, and do we put this T on this piece of pipe from 3 to 4? Or do we put it on the piece of pipe from 4 to 5? Or do we just say, fuck it, who cares, and not put a T on it at all? We got to figure out the T. The way that I was taught to do this, and it sounds really funny, but it gets you right every single time, is if you look at the direction of flow. Okay, so direction of flow is going this way. If you look at direction of flow, say we're talking about the pipe from 4 to 3, or 3 to 4, however you want to look at it. If I picture sitting on this pipe in the direction of flow, and I look behind me, so I'm a little guy sitting here, and I'm looking this way, I turn around and go, what fitting did I just come through? I just came through a T. So the pipe from 3 to 4 is going to have 1 T on it. And if I'm coming down from here like this, I turn around. Sorry, the water's going this direction here. So this is my little guy sitting here. in the direction of water flow this way, I turn around and see that there was a T behind me. So the piece from 4 to 5 gets the T on it. The piece from 3 to 4 gets the T on it. Does that make sense? A lot of guys used to get that all backwards about, oh, I don't know which fitting the T goes on. Which one does it go on? How do I do it? This sounds stupid to picture a little guy sitting on a piece of pipe and turning around and looking backwards, but it works every single freaking time. You know, just if you can't figure out which T you're supposed to use, do that, and that'll get you there. But now we got to take into account these T's and stuff. We didn't do that on the last one because I wanted to make it a little bit easier, but we're going to go to a new example. We're going to go here. Actually, I'm going to try to draw it in an isometric pattern so we can see what's going on. We've got a main going this way. We're going to rise up. Then we're going to run this way here and here. Okay? We're going to have 3 heads here. And we're going to have 1 here. We're going to figure out what is the flow and pressure needed at this point right here. This is our target point. Okay? We'll go 1 inch, 1 inch, 1 1/4. Let's say that this is like a center fed system, so it'll all be the same thing. So this is 1 1/4, 1 inch, 1 inch. Let's make this 1.5 inches. These will be a typical 12 foot. This will be a typical 6 foot. And we'll do a 2 foot riser nipple. Okay? Does that make sense? Okay, let's stick with K5, 6. And let's do, these are, let's say this is a light hazard building and our sprinklers are covering 160 square foot. So what is my minimum flow per sprinkler? It's light hazard, so what's the density of light hazard? 0.1. So what is my minimum flow out of each sprinkler? 16 GPM. Okay. So we know Q1 equals 16. What is P1? Q divided by K. 16 divided by 5.6 and square that. 8.2. Do you guys get that? Go 1. Okay. 1, 2, 3, 4, 5, and 6. Okay. So we want to know, we're trying to figure out P5 and Q5. That's what we're trying to figure out. Okay, so these all need a minimum of 16 GPM. Is our minimum. Okay, so we got this here. So P1 is 8.2. What is the friction loss? Do we have any fittings between node 1 and node 2? No fittings at all, right? So let's figure out what the friction loss is. 4.52 times our flow was 16.85 divided by 120 to power 1.85 divided by 1.049 to the power of 4.87. We got 0.08. Did you guys get that? Actually, if I follow rounding rules, it's 0.09. Do you follow that? So now P2 equals 12 times 0.09 is 1.08 plus 8.2 is 9.28. Do you follow that? So we'll just do 9.28. I'm kind of mixing my decimals. Now we need to figure out what is Q2. So Q is just K times the square root of P. So we do 5.6 times square root of 9.28. We'll say Q2 is 17.1, right? So now what is the flow from 2 to 3? What's that water flow going through there? 33.1. Right? So then our friction loss going through here is 4.52 times 33.1 to the power of 1.87 divided by, oh, no, it's 1.85, sorry. Divided by 120 to the power of 1.85 divided by, our diameter is 1.049 to the power of 4.87. Our friction loss per foot is 0.33. We said this is 12 feet. So times 12, as I get 4 pounds of loss through this piece of pipe. Do you guys come up with the same thing? Okay, so P3 is going to be 13.28. So I took P2 is 9.28 plus my 4 pounds going through there gives me this. Okay, now we're going from 3 to 4. Let's figure out what's the flow at 3. What? 20.4? Okay. I didn't check it. I'll trust you this time. Let's do 5.6 times square root of, what's the pressure there again? 13.28? Yeah, I get 20.4. Okay, cool. So we've gone here, as this is 20.4. Now, before I go and take on this one, I just want to hit, well, no, let's go ahead and do this. So, so we've got, now we got to figure out the friction loss from 3 to 4. So first, let's figure out the friction loss per foot. So our flow from 3 to 4 is 33.1 plus 20.4, or 53.5. Okay, that's our flow. Let's figure out our friction loss per foot. So we're just going to do 4.52 times 53.5 to the power of 1.85 divided by 120 to the power of 1.85 divided by 1.38 to the power of 4.87. Where'd my mouse go? There we go. Is 0.2 psi per foot. Okay. Now, how long is this segment of pipe? What do? We got to figure out fittings and everything else, right? So, so we've got, this here is 6 feet. Do we figure this T on this piece of pipe or on this piece of pipe? We're trying to figure out this T right here. Which piece of pipe does it go on? Yeah, it goes on 3 and 4, because if you were sitting on here looking at 3, you'd see a T directly behind you. in the path that you did. So you got to go to NFPA 13, and I think it is in chapter 23, where we have the equivalent foot table. I hope it's in 23 here. If not, we're just going to have to agree what an equivalent foot is for 1.25 inches. Where is it? Hey, check that out. Okay. So a T with a flow turned 90 degrees, which is what we have. 1.25 inches is, that's in feet. Okay. Where is it? 6 feet, right? So we go back here. So our total length is 6 plus 6, or 12 feet. So we do our 0.2 times 12 is 2.4. So P4 equals P3, which is 13.28 plus 2.4 equals 15. I'm just going to do 15.7. Do you follow that? Okay. And I got 53.5 gallons through here. Now I got to figure out what the heck I got to do with this side over here. We haven't talked about what we do when we have a difference coming through here. So I need to figure out an equivalent K factor of 6 to 4. What is my minimum flow to come out of this sprinkler? They're all covering 160 gallons or 160 square foot at 0.1 gallon density. So we need 16 gallons coming out of here. So I basically started the same way I did this one. We got 16 gallons. So we got Q6 equals 16. We got P6 equals, what did we say it was? 8.2. Do you see how I got that? This is a K56 head, 16 gallons. This one right here was a K56 head with 16 gallons coming out of it. And we said that P1 was 8.2. Do you follow that? Okay. Now let's figure out the friction loss from 6 to 4 so we can figure out what the pressure is, the pressures and flows at this point are right here. So we're going to do 4.52 times the flow. It's only 16 in this one because we're just doing the one head. 16 to the power of 1.85 divided by the C factor to the power of 1.85. The diameter in this segment of pipe from 6 to 4 is 1.38 to the power of 4.87. So I did that wrong. Oh no, it's 0.003. Did you come up with 0.003 per foot? Did you come up with that value, Scott? Or anyone else? Okay. I'll do it as well because mine looked funny when I did it. So we do 4.5. 0.003. Okay. So this plus our 8.2 is still basically, P4 here is still 8.2. It's 8.2003. You follow that? So I'm just going to use 8.2. Okay, now, principles in physics. Actually, we didn't do something else here. So we got 0.003. What is our length that our pipe is through? That's 0.003 pounds per foot. This was going 6 feet. But what is our equivalent length in here? We got 6 plus we said that the equivalent length was 6 feet there, right? So that's 12 feet. I think we did something wrong. I want to check something again. So this is, I'm going to put 12 feet in parentheses right here. Okay, because this is 6 feet of pipe plus 6 feet of a T fitting, so that's 12 feet. So we got 12 times 0.003 is still 0.03. And so P4 is still going to be 8.2. Do you follow that? Okay. Now, I'm not sure if we multiplied this by 6 or 12. So we had 0.2 psi per foot was the friction loss here. Okay, so our friction loss from 3 to 4. So we do 0.2 times 12 is 2.4. Okay, we did it right. Sorry. As I was making sure that we took everything right. So now we've got P4 here of 15.7 and P4 here of 8.2. You cannot have two differing pressures at the same point. So they're going to cause, it's going to balance to the higher pressure, which means that the 15.7 pounds is going to kind of go both ways. So I'm going to have more water coming out of this head than I actually need. We said that to satisfy this, we only need 16 pounds here, or 16 gallons. Let's get an equivalent K on this side of the main, as we got Q of 16 and P of 8.2. So we get our KEQ is going to be 5.6. This example sucks because the head and the equivalent are the same factor, but that's just what it is. Do you see how I did that? So we're trying to find the K. What you got? Q equals K square root of P. So K equals Q divided by the square root of P. So if I do these, if I get 16 divided by square root of 8.2, I come up with 5.6. You follow that? Okay, so I've got an equivalent K factor of 5.6 right here. So now I'm going to flow from 4 to 5. I've got 53.5 gallons here. I've got to figure what's coming from this direction as well. I've got a pressure of 15.7. I've got a K factor of 5.6. So my Q from 6 to 4 is going to be 5.6 times the square root of 15.7. And that equals square root of 15.7. That equals 22.2 gallons. 22.2. Do you understand that? So what's happened is we're basically hitting this head with more pressure than it needs. It causes it to over discharge. So this side of my flows and stuff this is going to give me 22.2 gallons. So I got 22.2 gallons from this side, 53.5 from this side. So what is my flow? So what is my flow from 4 to 5? I've got all the flow from this side and all the flow from this side. They're going to flow down that stick of pipe there. So that's 53.5 plus 22.2. So that is 75.7. Does that make sense? Okay, so that's the Q coming down here. Now we need to find the friction loss per foot. So our friction loss per foot is just our same formula. So we do 4.52 times the flow, 75.7 to the power of 1.85 divided by still C factor 120 to the power of 1.85 divided by we said this was 1.5 inch diameter, so 1.61 to the power of 4.87. I come up with, let's say that my my flow per foot, or my friction loss per foot here, is 0.2. Or we can do 0.19 if you want. Does that make sense there? Okay, now we got to figure out what length of pipe that this goes through, and do I have any fittings? So we're coming down here, and I've got to account for this T at the bottom of the riser nipple. So this is, my water flow is going this way. So I've flown here, so I've come through this T. So I got 1.5 inch pipe with a T. I go to my table and I go 1.5 inch pipe with a T is 8 feet. So now my total length, my L equivalent length, is 10, right? Because that T was 8 feet, right? Yeah, the T was 8 feet. So 10. So now my friction loss here, my friction loss total from 4 to 5 equals 10 times 0.19 or 1.9. Does that make sense? Okay, now we've got to figure out what the pressure is at 0.5. So I know my friction loss here is 1.9. What do I add it to? I had a pressure of 15.7 and a pressure of 8.2. We said you always have to balance to the higher pressure. So we use this 15.7 to get this equivalent flow on this side over here, which we determined to be 22.2. So I take P5 equals 15.7 plus 1.9, which is 17.6. And my flow at 5 is my 75.7. Do you guys see how that works? Yes, no, maybe? Cool. That's basically your hand calcs that you're going to do in a NISET Level 3 exam. If you can run through those different scenarios where you've got to figure out what the flow is based on your area of coverage and your density, and then you know your K factor, so you figure out what your minimum starting pressure is. Then you just figure out friction loss through the pipes, add fittings, add equivalent length and fittings if you need to. When you get to a junction point, so like we had, oh, I lost my mouse again. I'm going to try to use the highlighter here. So we had this junction point right here. You always balance to the higher pressure. So I had my 53.5 gallons coming this way. It needed 15.7 gallons. I only needed 16 gallons coming through here. We figured out our equivalent K factor because we knew that we really didn't lose any pressure through here. So our equivalent K factor was still 5.6. We took our 15.7 pounds times our 5.6 K. That gave us what our actual discharge is going to be out of this sprinkler. So that tells us that in order to get 18 gallons a minute out of this sprinkler, I'm going to end up with 22.2 gallons a minute coming out of this thing. But then we took our 22.2 and our 53.5, added those together because that's what's coming down this leg here. Figured out our friction loss with our total of 75.7. We were able to figure a friction loss of 1.9 pounds. We had 15.7 at 0.4, add 1.9 pounds, you end up with 17.6. So our total pressure was 17.6, our total flow was 75.7. Make sense? That's really all your basic tree calcs are that you're going to do on NICET level 3. Yeah, and if you kind of see how this starts to come into play, here's some practical scenarios just for what you guys do is, you know, let's say we've got a manifold, we've got an overhead system here, you know, let's say it's some grid. We're doing a warehouse here and we need 70 psi at 600 gallons. Okay, now I've got a rack system over here where I'm feeding rack heads. If I calc this so that this needs, say, 90 psi, well, you know it's going to balance to the higher flow or to the higher pressures. So I would be over discharging my overhead system by 20 pounds. I'd be flowing a lot more water out of it. So one thing you can do, and this is counterintuitive to what most people think, if they don't understand how calcs work, they're going to just keep opening up pipe sizes, say, oh, well, my 2-inch lines didn't work. Let's make them 2.5 so you can handle the over discharge. If I were to shrink maybe this pipe size here, as I had it a 6-inch, if I were to take this to 4-inch, now this 70 may go up to say 89. Okay? Now my pressures are closer to being equal. It's not going to over discharge things. So there's scenarios where making smaller pipe size is actually more beneficial to you than making bigger pipe size. Or let's say it's just reversed, as I've got a manifold here go up, have my grid system this way. Say I'm doing some crazy ESFR system that has in-racks with it. It's something crazy. You know, I've got 90 pounds here at 1,200 gallons, and then I've got to have some rack system here. Well, if I calculate my rack system with the way that I first calculated it, say it's only 50 psi needed at this base point here. I'm going to over discharge those racks tremendously because you have to balance to the higher pressure. So what I'm going to do as a good designer and not being a moron and just always going bigger pipe until the thing works, I'm going to go, hell, I got 40 pounds of pressure that I need to lose in this rack system. So maybe instead of these being 1.25-inch lines, I shrink them down to 1 inch. Instead of this being a 3-inch rack main, I shrink it down to 2.5-inch. Because I want to get this pressure here as close as I can to this pressure here. So again, bigger pipe doesn't always win. If you're doing a residential attic, you know, like you get some of these dry system attics and they're just a nightmare trying to calc. Sometimes smaller pipe is better because if you can look at what you're getting at your various points. I know this because I just had a job where I was helping a guy and he had some dry system. It was kind of sitting like this here. And then it did some funky loop around. And he had to basically do all this to get his 2,535 square foot. And his riser was right here. This ended up needing like 40 pounds here. And this, when it came through, was like 50 pounds. So it was over discharging everything like crazy, and he couldn't figure out how to work. He calls me up. He's like, dude, I've got 8-inch pipe in a light hazard attic, and I still can't make it work. Because he would open this up at over discharge, and things were going back and forth. All I did was I saw these two things. I said, well, hell, let's scrunch this down. Let's shrink this from his 3 to 2.5. Made these two pressures equal. Nothing over discharge, everything worked. So making pipe smaller actually made his system work when he couldn't make it work with 8-inch pipe. Does that make sense? That's a hard concept for guys to grasp. That whole balancing and smaller pipe is sometimes better. That's a hard concept to grasp. But if you understand this thing that we did right here, this right here, if you can understand this, you'll know calcs better than 90% of the guys doing design today who are just plugging in bigger sizes to make things work. Understand that there, and you guys will greatly improve what you're doing. How was that, Scott? Did that answer some of your questions, give you some basic run-throughs of what you're trying to get? No worries. Yeah, a lot of this, as I was trying to throw in a bunch of stuff into the time we were trying to keep it down to, so I didn't keep you guys all afternoon. But is a lot of this is just, once you get the concept, it's practicing the plug and chug. Is pick some scenarios that you have. And what I would do, and when I was teaching at the Fire Sprinkler Academy, is we would have them go through and do it by hand, and then go into their computer software, whatever they were using, AutoSprink, HydroCalc, whatever, plug it into the computer and see if they were getting the same answers. If they weren't getting the same answers, then they had to redo it. Because if you're doing a simple tree system, you should be able to get exactly what the computer gets within some rounding errors. Because I know like AutoSprink carries things out to 7 decimals. So where we were going out to 1 decimal here, AutoSprink goes out to 7. You're going to have some differences with that, because I wouldn't want you to carry things out that far. But that's generally what you're looking at. And again, if you can plug and chug and get these, you'll be able to get through your nice set 3. Go through and work through them. If you guys got any questions, give me a shout. We can always do this whenever. Sound good? Cool, guys. I'm going to try to stop this and see how big the file was, and then I'll send it to you via Dropbox. Okay, Scott? Cool. Take care, guys.